Hello YouTube, it is Danica,
And Jordan.
and we are here to talk about presentation 3 for our Engineering 460 Monte Carlo class. So today we are going to be talking about random generators, and for this one, this equation at top, we're trying to create a random generation of numbers using this equation at the top. So here, our initial x has to be greater than 0, and that's the seed. So a seed is something that is used to create that random sequence of numbers. And in theory, if you know the seed, you would be able to figure out all of the random numbers that are being generated. But anywho, so x of I is the pseudo-random sequence of numbers, and the reason it says pseudo is because you have that seed, and so you could, in theory, figure it out. Our a always has to be greater than 0, and that's the multiplier for whatever the devised number is. C has to be greater than or equal to 0 in this linear congruential generator, and that's the increment, so it's what you're adding on to it. M always has to be greater than 0, and that is the modulus that you're kind of modifying. And then the mod function is simply the remainder after the division algorithm. And so then our random set of numbers greater than 0 going up through 1 is going to be that x divided by the mod and going up until you have the amount of numbers that you want. And then the maximum period for the generator is going to be m. So here we're talking about maximizing the period of random numbers, and this image on the screen we took from our textbook. These are just common rules of thumb that we follow, and it's kind of devised from number theory. So C and M from our previous slide, they have to be relatively prime. So the greatest common divisor of C and M is going to be 1. And then a minus 1, so the previous a is a multiple of q for every prime factor q of m. And then a minus 1, so the previous a is going to be a multiple of 4 if m is a multiple of 4. Switching gears a little bit, this is talking about mixed linear instead of just the straight linear that we were talking about before. So in this case, the biggest difference is that the c has to be greater than 0, whereas before in just linear, c could be greater than or equal to 0. So typically for computer-generated random numbers, they're going to use 2 to the 31 minus 1 for m. And computers typically will run into overflow, which means that they'll start repeating that period if the number of random numbers exceeds this bracket, if it goes over that 2 to the 31st minus 1. So to avoid that overflow, Sraj method was used, and Jordan's going to kind of talk about that for a little bit.
So the Sraj method basically relies on you having your typical linear congruential generator, but also another value that's used would be the R. The R will reset the seed and using the original generator. So you're basically, instead of using the seed and just moving along, you're resetting the seed every time and then generating the number from that first seed that's been generated. So that's kind of your way to get around the overflow. It produces more results. Moving on. We're going to have our multiplicative linear congruential generator. This basically means when c is equal to 0. This is just going to be using just a and not using c at all. So for this type of generator, we want the a to be a primitive root of m if we want to try and maximize the period of the generator. And we also want m to be prime. These two things are also supported by number theory. These two things establish a maximum period prime modulus generator. So if both of these are checked off, then it will be the maximum period modulus generator. This can be seen with a few examples, but moving on, most of the time people will use 2 to the b minus 1 for their m in their generator. So typically they use 2 to the 31st minus 1 because that's typically the largest one they can get with numbers. Moving on, to really understand this, we need to understand what a primitive root is and what Mersenne prime is. So whenever you have a multiplicative linear congruential generator, you want a to be a primitive root of m. So to find the primitive roots of m, we just do if the result of m divided by a, where I is equal to 1 to m, produces a full period restarting on m, then a is a primitive root of m. So basically what that means is if you have m divides a to the I, so it would be a to the first, and then all the way up to a to the m. If a to the first is equal to a to the m divides a to the first is equal to m divides a to the m, then it is a primitive root. Secondly, we're going to be moving to Mersenne primes. Mersenne primes take the form of 2 to the b minus 1, where b is a prime. So typically this is just for producing large prime numbers. It's a quick way to produce large prime numbers because it's actually very hard to find large prime numbers because you have to divide by every single number before it. So your runtime for the program would be very long to actually find those primes. This is just a quick way to find large primes. And we also know that if a thing is prime, then your modulus generator will create a large period. So for our next one, we're going to have our theoretical test for random numbers. Basically what this is saying is that if you have two linear congruential generators that are exactly the same, so if you use the linear congruential generator twice in a row, let's say for x and y, we can expect them to be linearly dependent on each other for the same generator, no matter what the seed. So basically what this means is that they are reliant on each other, and this might affect your results for the test. So what we want to do is we want to use LCGs, linear congruential generators, that have relatively low overlap. Overlap is just basically if their periods overlapped if they started with different seeds. This is why typically they use larger numbers for m, because you have a larger period, and because the maximum possible size of a generator is m. So if you have a large m, then the generator is large, which means the overlap is less likely to happen, which could obscure your results. And finally, moving into the last part, when the dimensions of a variable that is randomly generated increases, the graininess increases. Basically what this means that if you increase the amount of dimensions of a variable, it will increase the distance between certain variables. So whenever we're generating random numbers, we want it to be a continuous distribution. What I mean by continuous distribution is that it has infinitesimal distance between one point to the next randomly generated numbers. We cannot actually do this with our generators. We are actually creating a discrete generation that's approximating a continuous distribution. Now, as the distance in between each one of the random numbers increases, then the graininess starts to affect your results. So basically just the graininess is the distance between consecutive random points. As the distance increases, the graininess increases. So we could say that if there is 0.1 difference between each random number, then we can only get 0.99 or 0.98. We can't get 0.981 or 0.991. It's kind of like limits your results and your accuracy of results. So we want the generators to be as close to continuous as possible. And with that, that is it.
Thanks for watching, guys.